All right, welcome everybody. We are going to go ahead and get started. It is 2 o'clock. I'm really excited today to introduce Heidi Reitmeier. She's my very first grad student, which is very exciting. And this is an exciting moment for her too. Heidi started as my technician working for me just after she graduated from the University of Minnesota Crookston uh, you graduated in fall of 2018. You started working for me in January of 2019. And shortly after that, Heidi started to pursue one of her big career goals, which was to get a master's degree. And I've been so, happy to work with Heidi on this project. And obviously, as you all know, the past year has been unlike anything we could have imagined it would be. But, I think with that, I will, I will let Heidi take it away and start telling you about what she's been working on for her master's research. So thanks. And Heidi, I'll turn it over to you.
Thank you, Lindsay, for that introduction. All right, let's get started here. So good afternoon, good Friday afternoon, everyone. I'm sure you're happy it's the end of the week. And thank you for coming to my thesis webinar today. It's on Minnesota phosphorus loss, how soil quality is only part of the story, and why modeling it can be improved by considering subsurface phosphorus flows. And like Lindsay said, I'm an MS student emphasizing in soil science in the land and atmospheric science program with chair advisor Dr. Lindsay Pease. So it's been an honor, and it's a privilege to be able to be this far in my master's program and to be able to present on this today. So to get us started here's a table of contents to go over the pieces of the presentation today. So introductions will be on environmental quality issues in soil and water, as well as Minnesota phosphorus index modeling and why the model is ready for an upgrade. The methods on how the MinPI works, my thesis objectives, as well as data collection for testing the model, the MinPI model, results of my studies and model tests with the collected data, the discussion afterwards on the implications of the gaps in the model, and then finally some conclusion remarks and statements. So here's the introduction. And by the way, this master's thesis is based on my research of up to 30 years of data sets that were combined in my soils research position, like Lindsay had mentioned at the beginning, at the Northwest Research and Outreach Center for the first time at the Research and Outreach Center where I work. And some of this data has been looked at for the first time as well. So there are these two environmental quality issues that historically have been studied separately until recently, and these are soil quality and water quality. Why am I trying to tie these two topics, seemingly different topics, together? Well, while investigating phosphorus loss risk, I knew that phosphorus, or P, tends to be a soil-bound nutrient, and this has historically thought to be the case. People thought, oh, phosphorus sticks to the soil. Well, this posed a curious area of research for me that involves both soil and water quality working together in order to prevent further P losses to the environment that cause water quality issues. On the topic of soil quality, soil P loss from agricultural systems will limit food and feed production in the future, with average losses of P due to erosion by water contributing over 50% of total P losses. Therefore, not only is P loss toxic for the aquatic environment, but the loss of it also means that we are running out of what we can apply as fertilizer adequately in the future for crop production, as this is a limited natural resource. And according to the same source that said this, on the slide here I have agricultural soils worldwide are to be depleted of phosphorus by between 4 and 19 kilograms per hectare per year. So that's soil quality. Moving on to water quality. And here's an example of what I'll be talking about. And this is Lake Erie, one of the US Midwest Great Lakes. That is a notorious example of eutrophication, also known as harmful algal blooms. And these develop in places like this example, Lake Erie and the Gulf of Mexico, due to toxic nutrient levels that cause anoxic or low oxygen conditions in these waters, creating a marine dead zone. These blooms can require restrictions on, fisheries, recreation, and drinking water uses of inland freshwater bodies as well, and therefore cause significant economic consequences. Eutrophication, along with climate warming due to climate change, are both profoundly affecting fish in many freshwater lakes. In Minnesota, harmful algal blooms have led to severe incidents, including human illness and animal deaths. Also, water quality impacts associated with eutrophication or harmful algal blooms include the following symptoms, like noxious algae, excessive aquatic plant growth, or the loss of some aquatic plants, loss of water clarity, low dissolved oxygen, which means loss of habitat for fish and fish food, as well as excessive organic matter production, which has a smothering effect in the water, just to name a few of these effects of harmful algal blooms. So this hypoxic situation in the US Midwest, what can be done about it? Phosphorus loss risk assessments can be beneficial and even necessary in order to predict whether farm management practices are sustainable in terms of their P-loss risk to the environment through phosphorus fertilizer applications. And they can also help prevent unnecessary P-loss to receiving waters, thus preventing algal blooms. These P-loss risk indices can help understand the risk of P movement and either encourage or discourage phosphorus fertilizer application to crops based on the risk of P movement. And inaccurate P risk assessment can have serious economic, environmental, and biological effects in the environment. So it is helpful to have a P-loss risk assessment tool to deal with this. One example of a P-loss risk assessment calculator is the Minnesota Phosphorus Index model. And here in the middle of the title, I have it's a copy of the application logo. This application was developed through the University of Minnesota, so that's why it's maroon and gold, as you can see here. And so this Minnesota Phosphorus Index, or MinPI, determines P-loss risk in Minnesota. It's required for writing nutrient management plans for cost share dollars for conservation models from the USDA NRCS. This index has not been updated since the year 2006 and is based on southern Minnesota data. So therefore, it may not be representative of conditions in the northern half of the state. For this thesis, the MinPI project has reviewed the overall performance of the MinPI model across Minnesota's broad range of agricultural landscapes to ensure its usability as a means to estimate P-loss. So it is to be updated in the future. Please stay tuned for these updates. Hypotheses that I had while working on this thesis, I had two of them. So here's the first one. The current MinPI model requires updates. And then hypothesis 2, soil quality is totally crucial to P-loss risk. I thought going in, so because phosphorus is attached to soil, I think soil quality is super important to phosphorus loss risk prediction. And the soil quality parameters that I wanted to look at in particular were tillage practices, as well as, I'm not sure why it's not showing here, tillage practices, and then the other one was organic matter percentage. Soil quality parameters that are in the MinPI model inputs. So it was possible to analyze soil quality trends as they relate to P-loss risk based on these two soil quality parameters. So my thesis objectives then, based on these hypotheses. So I wanted to discover how the current MinPI model thinks about phosphorus loading of water bodies through soil erosion based on soil quality. And knowing this can assist with further model developments based on where errors in these predictions can be found as they relate to the need for subsurface tile phosphorus loss data. All right, moving into the methods section here. How the MinPI works. It's used for farm nutrient management planning and watershed planning to control phosphorus loss. And like a model needs, it needs inputs and outputs. It needs inputs to create outputs. And so the inputs that go into this model include distance to water, because distance to water can, if you're closer to water, that can increase your P-loss risk because we don't want that phosphorus to get to the water. Soil test P or STP level, erosion and farm management information, such as fertilizer, P fertilizer and manure rate and application method, tillage type and direction, as well as county location and crop rotation. The outputs that the model creates once you have these yearly crop data entered are sediment delivery, particulate P, rainfall soluble P, and snowmelt P. And overall calculates an index of P-loss risk on a scale of 0 to 6 or more, based on the inputs you gave the model. And these three P-loss, these three different types of P-losses are also known as routes or pathways. So just to give you an idea of how phosphorus is moving in the environment, it moves in different pathways. Okay, so more about how the MinPI model works. So, and to break down these outputs, sediment delivery is given in kilograms per hectare per year. And we have pathway 1, which gives us particulate P lost via erosion by taking erosion rate times sediment delivery times total soil P. Pathway 2 gives us risk of soluble P lost via rainfall runoff by taking the rainfall runoff rate, multiplying it by both soluble soil P and applied P. And then we have pathway 3, which is snowmelt runoff rate times P and plant residue plus winter applied P to give us the risk of P loss via snowmelt. This goes back to the freeze thaw that can happen with plants in the environment, that when plant tissue can freeze and then release that contained phosphorus in those plant cells after the winter thaw. So that's what that's based on. So with these three pathways calculated, a P-loss risk index value of 4 is considered high according to the model, but a value of 2 or 3 may also be appropriate for a given situation, say if you're closer to a body of water, for example. And note that these are all surface P-losses, and yes, surface P-loss is critical, but we are missing the subsurface P-loss components beyond just erosion and surface runoff, even though those are traditional sources of phosphorus. So the current MinPI used with the data looks like this, and we see that the interface is a bit dated. It has been 15 years now. So another reason why we'll be updating this. But anyway, so what you enter for each crop year from your farm records, you would enter your all your fertilizer data, whether it was manure or synthetic fertilizer, your soil test phosphorus data, any tillage that was done in the fall or spring, and hydrous ammonia if it was done, and then crop information like crop planted, cover after planting, and crop yield information. And once, and the values in red, those need to be entered so the index will work. There at the bottom, you get calculated your average MinP risk index, as well as the category that it's in. You get average sediment delivery, and then those 3 pathways like I talked about for each crop year that you enter, as well as the average at the very end. So this is how it works, and it is a surface-based model, as we've seen. What I'm hoping is that this will be a more edge-of-field based model to include subsurface drainage when predicting P-loss risk, even though surface data is important for phosphorus loss risk, based on information from some of my that occurred across some of our data was tile sourced. So particulate P is still important and valid for predicting phosphorus loss risk, but it's not everything. So it has been a while. We have new understanding. This model is going to be updated with both surface and subsurface P losses. And then an example of how this model works just in action, so to speak. So we have these 3 fields at the Northwest Research and Outreach Center where I work. We have fields 1, 5, and 8 here across 30 years between 1988 and 2018. And I actually have graphed, even though you do get an average, as you see in the bottom, average for each field, for each of these pieces of information, you can also see your individual yearly. And that's what I have on the graph here at the top. So we can see that field 8 consistently over these 30 years has the highest min-P index as compared with the other 2 fields, fields 1 and 5 here. So this is showing just how that index is working with a few of our fields, for example. Data collection that I did, I requested data from across the state of Minnesota to test this model. And these are the sources across the screen here: Discovery Farms of Minnesota, the Minnesota Agricultural Water Resource Center, the Minnesota Department of Agriculture, Northwest Research and Outreach Center, and the University of Minnesota. Of course, last but not least. So these were grouped by Minnesota region and statistically analyzed for trends in nutrient loading and farm management data. I'll be showing those figures soon here. Here are the geographic locations of these sources across the state of Minnesota. We have all these pinpoints showing the general locations of where these are coming from. There is a total of 24 sites from 18 total counties, but here I have colored the general sort of regional locations of where these data are coming from. Red for Discovery Farms, as you can see, yellow for Rit River sites, coral for Wilkin County sites, purple for Lamberton sites, and teal for Waseca, Minnesota sites here. So, and then Minnesota regions analyzed. So we have 5 main regions that were studied. Central Minnesota, as you can see, labeled on the map to the right here, we have those 2 kind of pinkish purplish colors in the middle of the state there for central. Northwest Minnesota in blue, South Central Minnesota, like Blue Earth and Waseca counties, between the southwest and southeast parts of Minnesota here. So imagine that there's a central region there in between the green and purple there. Southeast Minnesota, that's purple, of course, and then southwest in the green there. So 5 counties that were analyzed in total. And then moving on to the results from the data analyses. So I'll be going over figures that involve statistics, and I'll just briefly go over what those are about. So nutrient loads will be from combined raw surface flume and tile flow data to give an idea of the total edge of field phosphorus loss. And then the graphs that we'll be seeing were made in a statistical online program called JUMP. It's a program based in SAS, if you've heard of that. And then so I'll have box and whisker plots that will show the test of the model prediction accuracy, and then non-parametric comparison graphs to show tests of variabilities across the state. And we'll go through those as we come to them. All right, variability across the state of Minnesota with these 6 variables. So, and they'll be presented in this order in terms of variability in precipitation, runoff, total suspended solids yield, particulate phosphorus or PP yield, dissolved orthophosphate or DOP yield, and then finally total phosphorus or TP yield. Looking first at precipitation in millimeters per year across Minnesota regions, across 20 years of data, so from 1999 to 2019. We have, so on the y-axis here, between 400 and 1400 millimeters per year precipitation. And then graphed with the 5 Minnesota regions here: Central Minnesota, Northwest, South Central, Southeast, and Southwest Minnesota. The N equals the number of data points that are showing in each of those regional categories. So that's what that N variable means. And then just a quick brief overview of statistical understanding. If for some of the audience that may not, a category of data or a data distribution of data has its own letter assigned to it. That means that that data set is statistically statistically different or unique enough from the rest of the data sets. So for example, here we can see that Northwest Minnesota has its own letter, a B. It's the data in that set is statistically different enough. And to get really technical, has a p-value of less than 0.05. I'm having a blank, but it has a low p-value, so it has to be 95%, within a 95% accuracy, that's statistically different from the rest of the data set. So Northwest Minnesota showing up different here. The other ones all have A's, so they're not particularly interesting in terms of precipitation, although we do see that Southeast Minnesota is having some of the broadest data distribution. It has some of the highest precipitation according to this figure. The runoff data in total edge of field surface and tile in millimeters per year across these 5 regions and 20 years again. So we see across along the y-axis here, the runoff in ranging from 0 to 550 millimeters per year, graphed with these 5 regions again. And what we see here is that Northwest Minnesota, it has its own distinct, unique. It's statistically different from the rest of the data because it has its own letter. Same with Southwest Minnesota. It's the only one with the letter A, and so this one being the highest in runoff, it got its own letter in statistically speaking. And then the other, well, and then South Central Minnesota as well. That one is also an A, so it's like Southwest Minnesota in terms of how different it is from the other regions. Central Minnesota and Southeast Minnesota are, when they have both letters, that means that they're kind of intermediate, or they have characteristics with the other regions, but they're not statistically significantly different enough from the other regions. So, but we do see that the northern part of Minnesota and these 2 southern parts of Minnesota are showing up as different in this runoff variable, for example. So it's good to see the variability just because the MinPI model was just based on southern data. And so when we can get a glimpse of northern Minnesota data, that is more inclusive of Minnesota. Total suspended solids in total edge of field surface and tile yield in kilograms per hectare per year across Minnesota regions across 1999 to 2019. We see along the y-axis here 0 to 3,000 kilograms per hectare per year. And there's a similar thing going on here where Northwest Minnesota data is looking pretty clustered and pretty low, but and yes, it is statistically different according to the Dunn method for joint ranking of the difference between all these regions. And then we do see Southeast Minnesota does have high total suspended solids here as well, but it's not statistically different from the rest of the data. Okay, particulate phosphorus. And then the other one, dissolved orthophosphate yield, will look kind of interesting together. Looking here at particulate phosphorus, total edge of field surface and tile yield in kilograms per hectare per year across Minnesota regions for these same 20 years and same regions. We see along the y-axis here, particulate phosphorus ranging from 0 to 2 kilograms per hectare per year. And Northwest Minnesota obviously it's different again statistically from the rest of the data. So is Southeast Minnesota with the highest data distribution here, as well as Central Minnesota. That one is statistically different from the rest of the data as well, along with Southeast Minnesota. But we do have, as you can see, those 3 outlier dots. If you ever see dots above a box plot, those are outliers from the main data distribution. All right, so seeing some variability with particulate phosphorus, but not quite as much as dissolved orthophosphate. So we do see that the DOP yield here, and it's also total edge of field surface and tile combined here in kilograms per hectare per year across these same parameters. So dissolved orthophosphate ranging here from 0 to 1.6 kilograms per hectare per year per Minnesota region. We see that Northwest Minnesota has its own, it's statistically different in the data distribution as compared with the rest of the data sets here. Southwest Minnesota has some of the the other regions, central, south central, and southeast Minnesota, are not statistically interesting. They're kind of, they share letters from other categories, but they don't have their own letter, so they're not as quite as different. But we do see a variability between these two. And so when we look at total phosphorus and total edge of field surface and tile yield in kilograms per hectare per year, again across these same regions and years, ranging here on the y-axis 0 to 3 kilograms per hectare per year for total phosphorus, we see that Northwest Minnesota has its own, it's statistically unique from the rest of the data sets again. So is Southwest Minnesota. And so seeing that difference again here between, the northern part and the southern part of Minnesota, we're getting sort of a glimpse of what's varying in these variables across Minnesota. And so, like I said before, the MNPI is only based on southern Minnesota data. Well, there's some variability, as you can see, across the state in terms of these variables. Now we'll hop over to trends across Minnesota in terms of these same variables: precipitation, runoff, TSS yield, PP, DOP, and TP yields. So the same order of everything. And the hypothesis for these graphs that I have, or that I had, based on what I would expect these graphs to look like, is this. So according to the MNPI model, very low is defined as having a MNP risk index of between 0 to 1. So I would expect the data to be somewhere in that range. Low is between 1 and 2 MNP risk indices. So it should be, higher than the very low, but lower than the medium. Medium ranges from 2 to 4, as you can see on the top, MNP risk indices. And so that should appear the highest when you're thinking about phosphorus loss risk, if it's deemed medium P loss risk as compared with the other categories. So it should have sort of this stair step. It should kind of stair step visually between each increasing category. However, some things will be curveballs here. So here's Minnesota phosphorus risk category graphed with Discovery Farms data, total edge of field runoff in millimeters per year, ranging from 2010 to 2019, so about 10 years of data here from the data set, all the data sets that we had, but similar trends were showing. And we see that the runoff is ranging here on the x-axis from 0 to 600 millimeters per year. And when it's graphed with the MNP risk category here along the y-axis, we see that the very low category is on its own maybe not that interesting, but when we compare it to the low category, that low category, it's, and here and then we do have red and blue here. So surface is red, edge of field surface plus tile is in the blue. So that's how these boxes are distinct from one another. And so the low category, as we can see, is the widest data distribution here for runoff. And it seems like there could be some over predicting going on when we're trying to predict MNP risk based on runoff. So, because the medium category, that is showing that runoff is the lowest for that medium category of PLOS risk. So not seeing that stair step appearance here with the runoff figure here. And then we're looking here at total suspended solids from Discovery Farms data in kilograms per hectare per year, ranging from 0 to 3,000 across these roughly 10 years or so, 2010 to 2019. Graphed with the MNP risk index categories, we see that there is a general trend that looks to be what we would expect between each category. So, very low steps up generally to low, and then low steps up to medium. Although we do have a few of these dots that show outliers in the data, but it's not as striking of a misprediction as we saw with the previous figure. So we do see that general, with these main box and whisker plots, we see that general sort of movement from low to high. here. And this is not, to me, this was not surprising because the surface data is seemingly caught by the MinPI model. And this model does run the Russell 2 equation, which is the second version. The Russell 2 is a calculator of soil loss. And so when this MinPI risk model is running this soil loss, equation in the model, it's not surprising to me that the total suspended solids are being caught as a surface data variable, because those are linked with it's like an erosion variable. It has to do with soil loss prediction, and so there's total suspended solids being predicted a bit better here, as we can see. And then looking here at Discovery Farm's particulate phosphorus yield, ranging from 0 to 2 kilograms per hectare per year across these same years, we see that the very low steps up to the low, but then drops down to the medium category, which again is not really what we would expect. We would expect that medium category to be higher than the low category based on the hypothesis and based on what the MinPI model would, based on where the MinPI model would traditionally categorize phosphorus loss risk. So, and it's varying even less than, I would say, dissolved orthophosphate again. So dissolved orthophosphate here ranging from 0 to 1.5 kilograms per hectare per year here along the x-axis, graphed along with MinPI risk category on the y-axis here. We see that the very low is lower than the low because that the box and whisker plot is not stretched out as far as that low category. So, but we do see that that low category is stretched out quite a bit with the data distribution as compared with the medium category. It seems like the medium category is even maybe about half the data distribution of that low category, which is not what we would expect based on the hypothesis for these figures either. And then lastly, total phosphorus yield ranging from 0 to 3 kilograms per hectare per year across these 10 years of Discovery Farms data, again, graphed with Minnesota phosphorus risk category. We see that the very low is actually looking to be to have the widest data distribution. So it's stretched out the most. It has it's including the most data points in that category for range of total phosphorus. Low is lower than very low, and that's not what we would expect. Well, the surface is running higher than very low, but not the edge of field data here. So, but they look about the same otherwise. It does seem like the very low is a bit overpredicted for total phosphorus. And then medium, of course, as we've seen before, it seems like that category is underpredicted based on this figure for total phosphorus, because that box is the smallest for the medium category. So here is a figure showing some of what's going on with the data. So what we see here is this figure is showing, so on the x-axis, the assigned risk category that I would give to the data, that the total phosphorus data, based on where I would expect it to be, knowing the index categories for each. And so, I gave data very low, low, medium, whatever they should be based on total phosphorus, because the model, like I said before, is trying to get at total phosphorus based on those three pathways that I talked about earlier. And so knowing that, what we can see here is that the very low category in red at the lower left is 49%, and it's along this one-to-one line. So anything on that one-to-one line is doing what it's supposed to be doing. It's predicting the way it's supposed to predict between assigned category and Minnesota phosphorus index category. It's not anything along that line is not deviating from what should be done for index prediction of phosphorus loss risk. So 49% of the time for very low, that's predicted right. And we see for the very low, it's 4.3%, and then medium for 1.4% along this line that you can see. But anything else, all these other percentages going above this line, below this line, those are beyond what is the expected prediction. So the percentages above that below are under predicted. And so we do see a bit of both going on here. I would say there's probably more over predicting going on than under predicting phosphorus loss risk with the data, but there is a bit of both. And we would like to be closer to that 1-to-1 line when we're thinking that a risk should be something, and the model is telling us that it should be something. So, and then here's an example of mean P risk category versus soil test phosphorus. And this soil test phosphorus is in ppm Olsen P. So, and I have an equation up here showing how we converted any Bray values to Olsen based on this reference. So we see here that Southwest Minnesota in orange is ranging, it's higher than the rest of the data, as we can see, even higher than the medium category here. So, you know, this is showing us that even when soil test phosphorus is, you know, is the highest in this data set, as we can see, it's here on the x-axis, is ranging from 0 to 50. We have this range of maybe somewhere between 30 and 50 here, STP, soil test phosphorus for Southwest Minnesota, and that's even ranked higher than the medium. So here's an example of where overpredicting is occurring, because it shouldn't be in the low category. If it's, you know, if it's higher than the medium, why is it in the low category? It really should be in a higher category if the data distribution is that much larger than the rest of the data, as we can see here. And just a note too, a quick note about soil test phosphorus. So going back to kind of soil chemistry basics. So Olsen P, that's a test that's done with soil test P that's in a calcareous soil situation. Bray is for soils that are somewhere between alkaline and acidic soils. So that's why we had to do some converting, because some of the soil test phosphorus data we had had a Bray. It was in the Bray instead of the Olsen. We had to do some converting with that. So that's how we did that. But anyway, over predicting is happening. Oops. And then looking at this figure, we see that the discovery farm's total phosphorus ranging from 0 to above 4 here, kilograms per hectare per year for these 9 years of data, graphed with Winnipeg predicted total phosphorus ranging from 0 to 5 kilograms per hectare per year here. We see that, and this is all graphed with fall tillage, so chisel or heavy disc in blue, or the no fall tillage in red. And what we see here is that this is showing us that we do have the highest total P with chisel or heavy disc, but we should be seeing a closer to 1-to-1 ratio between predicted and actual P losses here, because we do see that several of these data points are, I mean, they kind of cluster at that lower left corner of the graph, but then, you know, even though we're trying to draw this line of best fit through the data, we have some points going above and below these lines of prediction by the model. And so we would hope that in the future, that 1-to-1 sort of prediction between actual data and predicted data for total phosphorus would be closer to 1-to-1. May not be perfect, but we want it to be closer. So, and then similar line of thinking here with spring tillage, we see that spring tillage does have an effect on, the type of it has an effect on total suspended solids yield. We see that the chisel plow has some of the highest total suspended solids yield. Here we have it ranging from 0 to 3,000, just to give a sense of the range of this figure, 0 to 3,000 kilograms per hectare per year. So chisel plow does seem to cause the most total suspended solids yield. As you can see, compared with the other two types of spring tillage here. Disc or field cultivate has the lowest. No spring tillage has it has some. It's getting close to that chisel plow amount, but it's not as much. And it's interesting because we do have a few of these outlier points showing above the no spring tillage box and that box and whisker plot there. It's called. Those dots are outliers. I think those outliers are kind of neat and interesting because I don't know, there's some data that's showing up there for TSS yield for no spring tillage. So we can talk about that here. So examples of exceptions to the rule that not all soil quality goals equal P-index goals. So here on these green dots represent county data that was overpredicted by the MNPI model. And what we see is that spring tillage can be overpredicted by the model, even when there's no spring tillage. So yeah, so no spring tillage. We can even have overpredicted phosphorus loss risk in a no spring tillage scenario. Looking here at the middle figure here with total phosphorus graph with Minnesota County overlaid with cover after planting greater than 20%. And I think that the cover after planting, when it's put into the model as greater than 20%, that could skew some of the data, I think. But theories aside, we see that some of the total phosphorus yield is some of that overpredicted, those overpredicted sites, data sites, are showing up in an interesting way. So like we see this line moving across those highly predicted sites for total phosphorus based on the cover after planting over 20%. So maybe if that's inputted into the model, that could be over predicting our P-loss risk. That's another finding. The third one here on the right, we see that county site gradient in percentage versus county predictions of phosphorus loss risk. I thought it was interesting that comparing the non-overpredicted P-loss risk counties and the overpredicted P-loss risk counties, we see that those green dots are appearing at the 3% mark. So 3% gradient or above seems to have some overprediction going on with phosphorus loss risk based on the current MNPI model. So three things that could be overpredicting phosphorus loss risk based on the current MNPI model. Some of these things are surprising. We can see it with no spring tillage. We can see it with cover after planting even being high. We can see it with gradient change. So I wanted to include those three here to talk about that. There are exceptions to the rule that that soil quality goals equal P-index goals, because we can still have a high P risk no matter soil quality. And just a note about the cover after planting in the middle here, that's including organic matter content as well. That to get at both what's happening after a crop year in terms of all this fall and spring tillage that was done. So that's referring to some of that organic matter questioning I had before. A note about that. So moving on to discussion. So after looking at all these graphs and thinking about it, particulate P varies less across Minnesota regions than dissolved ortho-P or DOP. This could be a concern for a P-loss risk prediction model because it should be able to capture DOP loss as well as particulate P if DOP is varying more. Particulate P is more adequately predicted by the MNPI model than DOP. And Southeast Minnesota tended to have higher reported loads of both dissolved P and particulate P according to all the nutrient data that was gathered. This could be a climate issue of runoff induced by precipitation because we did see that precipitation was higher in this region of Minnesota. Minnesota does have variability in precipitation, as we saw. So we have seen how particulate P and soil erosion are modeled by the MNPI, but not so much DOP, an exception to soil conservation. Oh, and then another note about southern Minnesota. Besides the climate issue, there could also be some landscape gradient component to that region as well, to cause higher runoff levels and nutrient loads. For further discussion here, the current model seems to overlook high soil test P levels, as we saw, and management practices entered into the model might prevent seeing high phosphorus problems as a result. Even, for example, changing cover after planting to greater than 20% across multiple crop years. we see that, you know, there's something not being caught there, and changes in farm practices may only change phosphorus loss slightly. So, you know, phosphorus loss may be overestimated or underestimated at times because it may not be currently sensitive enough to all farm practices. Conclusions. So revisiting my hypotheses introduced in the beginning. Hypothesis 1, that the current MNPI model requires updates. This is accurate. Hypothesis 2, soil quality based on tillage and organic matter content is totally crucial to phosphorus loss risk. This is inaccurate due to some data observations. So while total phosphorus is most correlative to TSS yield across the data, its risk prediction is distorted by percent gradient and by percent cover after planting in the MNPI model. My recommendation here, so revisiting these 3 pathways, loss via erosion, soluble P loss via rainfall runoff, as well as snowmelt soluble P, we see, I have another pathway recommendation, and this is, I'm just going to call it pathway 4. Subsurface drainage discharge volume times label P plus applied P equals risk of P loss via subsurface load. So similar to the load equation, I'm hoping to try to capture subsurface drainage P loss with some type of loading equation like this. And that's what I'm recommending. Conclusion, the MNPI focuses more on surface level predictions rather than specifically outputting subsurface phosphorus loads. However, these small yet soluble P losses are environmentally important, even if they are not always agronomically important. An updated MNPI will be more equipped to detect both surface and subsurface losses of P than it currently is, since it was last updated in the early 2000s. So both phosphorus loss and soil quality are important considerations when it comes to, you know, land management and nutrient management. Both of them determine overall agroecosystem health. Too little of both leads to inadequate crop production and yield. Too high of P loading can lead to overgrowth of harmful algal blooms, as we've talked about in receiving waters. The health of soils and waters are both integral to the health of agronomic productivity. And to drive this point home, soil quality is important in P management, but we need to see the whole picture. Phosphorus loss via surface loss and phosphorus loss via subsurface drainage. And while we know that runoff can move soluble P above the soil, we equally need to know what moves below the soil. So to finish off this presentation, here is a photo from the Northwest Research and Outreach Center up in Crookston, taken fall of 2019. And when soil quality is preserved in its overall structure, phosphorus loss from surface erosion can potentially be reduced in severity. However, in indexing subsurface phosphorus flows could help prevent elusive phosphorus losses below the soil surface. With a broader understanding of phosphorus loss risk, farmers and their advisors may be able to utilize the upcoming MNPI updates for maximizing their operations while minimizing phosphorus loss harm to the environment. Acknowledgements I would love to make here to my U of M graduate committee, Dr. Lindsay Pease, Dr. Melissa Wilson, Dr. Heidi Peterson, and Dr. Paolo Pagliari, 3 of them in the U of M Soil, Water, and Climate Department, of course, and then Heidi Peterson from the Sand County Foundation in Agricultural Research and Conservation. Further acknowledgements, of course, for the MNPI project data sources that I had mentioned before, and listed here as well. The MNPI project funding source with the Rapid Agricultural Response Fund, U of M Student Research Assistant Peyton Moss, and last but not least, MNPI model software updates to come with Dr. Dario Canelon, Senior U of M Software Engineer. Thank you very much for taking the time to listen to my thesis presentation today on Minnesota phosphorus loss, how soil quality is only part of the story, and why modeling it can be improved by considering subsurface phosphorus flows. Thank you so much, and my direct email here for any specific questions is also provided here. And I'll just say that scientists can change the world by bettering it one study at a time. And my husband said that after hearing me practice, so I wanted to share that at the end here. Thank you.
Great. Thanks, Heidi. And if anybody has any questions, we do have a few minutes for questions here before we go into the closed portion of the defense. So feel free to type them into the Q&A box if you have any questions. So and thanks everybody for listening and for showing up, being here. So Heidi, it looks like you have your first question. Yeah.
Yeah, so Kyle is wondering, well, what was my most surprising finding while working on this project? The thing I was most surprised about was that my hypothesis too was rejected. I thought soil quality was so important to phosphorus loss, and it doesn't tell the whole story. So that's what was most surprising when I was looking at the data. That's my answer to that question. Thanks, Kyle. How is phosphorus important to soil quality? Is another. That's a good question. So phosphorus is a cycling nutrient in the soil, and there are multiple nutrient cycles happening in the soil simultaneously, and phosphorus is one of them. So and there are microbial things going on in the soil when phosphorus is cycling. So I don't have a really good answer to that, but I think that phosphorus is one of those. It's one of those key nutrients that, of course, supports crop growth and the biogeochemical health of the soil and all the microbes that are living in that environment. So there's this huge web of dynamics going on but phosphorus is just one component in that web of dynamics in the soil. Exudates that are trying to drop phosphorus in the soil, those could help, bind soil together. There's some, organic matter that contains phosphorus that, we know that organic matter is good in the soil and good for crop growth when it's present, like for example, in our mollisol soils, they're rich in organic matter and nutrients. So that's the long and short of it, of my answer to that question, I think. Thanks for the question. Did you look at another question here? Okay, there's another question here. Did I look at any of the original validation data, and did I speak with one of the original developers of the MinPan model? I looked at some of the original validation data. I've seen John Creeps. I've seen that name. I've seen John Marcoup's name. I have not directly spoken with him though. I've just seen the validation data papers and his name on them.
Well, and I guess if no one else has any other questions, I think we can wrap it up here. And yeah, thanks again, everybody, for being here. And yeah.
Thank you so much, everyone, for coming, and have a great rest of your Friday and weekend.